You can also take this further. So say you have your data right here, and you want to determine which of these linear separators is optimal. And this is the basis for what's called the support vector machine. So what the support vector machine does is it optimizes over all the points at the same time instead of optimizing over a single update like Mira does. And its goal is to maximize the margin right here. And so what the support vector machine does is it picks, it not only goes through the points iteratively, but it considers all the points at once and picks the separating hyperplane that maximizes this margin. And this optimization actually looks a lot like Mira, except of course it's done for all the points. And it turns out that the magnitude of the weight vector is related to the this margin right here. So instead of maximizing the margin, you're actually be minimizing the magnitude of your weight vector right here, subject to the constraint that that your feature vectors that your weight vector correctly classifies the data. And SVMs are used very widely in practice in general. And this is the optimization. And it also turns out that when you have noisy data, the SVM looks a lot like the Mira case with a cap of C on the weight updates that you make. Yes?
So exactly what's the margin in this diagram? And like, how does it depend on where the hyperplane is?
So the margin is defined as this value right here. It's not showing up. Yeah, so the margin is defined like that, and so this relates to your hyperplane because if you instead had a hyperplane right here, then your margin would look like this. You take the points that are closest to the hyperplane. So these are your 2 points that are closest. And then your new margin will look like this, and this margin is smaller for this hyperplane. It's hard to draw with this pen, but and so you want to pick the hyperplane that maximally separates the data, so that the distance between that hyperplane and the closest point is maximized. So you're maximizing the minimum distance between the hyperplane and the points.
Isn't it just achieved by making the hyperplane really far away? Like if my hyperplane was the y-axis or something, wouldn't it get an even larger margin?
So it's considering on both sides. So if your hyperplane was right here, then you would have a nice and large margin for all these blue points, but the red points would have a negative margin.
Oh, I see. Okay.
Yes?
Why do you multiply the thing that you're minimizing by 1/2 in both English and SVM?
That's just a convention because when you take the derivative, then it'll look nice because when you take the derivative, then you'll multiply by the exponent right here, and it'll just look a little bit nicer. But it'll become the same optimization problem if you remove the 1/2.